Okay, so what I want to do today is I want to talk a little bit about combinatorics. How many of you have seen some combinatorics? Since we've done some combinatorics in this class, everybody's hand should be up. Bless you. So how many of you have done any basic probability? Okay. So a lot of times the two subjects are very much related. And you want to try to calculate how many ways can something happen? What is the probability something happens? And so we need a few of the basic building block functions. I apologize if you've already seen these before, but in the interest of completeness, it's worth just going over them very quickly and then trying to do things that are a little bit more interesting. And we will get to my favorite math riddle as we do this. Oh, it's interesting. It seems to be swiveling when it's not connected. I'm not quite sure why it's swiveling when it's not connected, but interesting. I now am quite curious as to what that connection does. Oh, it makes it stop swiveling. Okay. Oh, I feel like Mr. Rogers. All right, come on. I'm sorry? Interesting. Maybe I should just leave it disconnected. All right. Wow, that is interesting. Interesting. All right. So we'll be just, I think, using a certain part of, I'm sorry? Unplug it. Unplug it, I know. But I'm just worried that if I unplug it, it's somehow not recording. That it's maybe, somehow it's maybe the audio is going and the audio might have been lost. All right. And so that's, I do want to, okay, now it's working again. All right. Technology. Okay. So, basic combinatorics. So we've talked about n factorial before. This is n minus 1, 3 times 2 times 1. If n is greater than or equal to 1, 0 factorial is just defined to be 1. It's the number of ways of arranging n objects when order matters. NPR, which is some old notation, is n factorial divided by r factorial. It's n minus 1 down to n minus r minus 1. It's the number of ways to choose r people from n when order matters. So there is a difference between being the president and being the secretary. Whenever you have problems like this, you always want to make sure you count the right way. How should I view n? What's the right way to view n here? Yeah, but I mean, when you look at how everything else is written, how should I really write n? So it's a more unified presentation. I have n minus 1, n minus 2, n minus 3, n minus 4. How should I view n? N minus 0. And when you view it like that, hopefully it's a little bit more clear as to why you stop at n minus r minus 1. I have r things, but I start counting at 0. So for those of you who have done some computer science, a lot of times you do start counting with 0. Then we have NCR, or n choose r, which is written like this. This is NPR divided by, oh, I'm sorry, this is not r factorial down here, sorry. This is n minus r factorial. My apologies. This is NPR over r factorial. And this is the same as n factorial over n minus r factorial, r factorial. This is the number of ways of choosing r objects from n objects when order matters. So one way to see this is I first choose r objects from n when order matters. And that's how many ways to do it. Well, now that I have these objects within order, I want to see how many of these orderings are equivalent to the same set of people. Or equivalently, if I take people where order doesn't matter, how many ways can I institute order? So any fans of Lord Business from the Lego movie, how many ways can I put in order? I have r objects. I have r factorial ways to order them. Okay? And so n choose r times r factorial should be this number. So this is just this number divided by r factorial. These are the basic combinatorial objects. One of the problems we were looking at, I think, was the following. Consider the following. The sum n goes from k to infinity of n choose k 2 to the minus n. If you had your choice, what value of k would you? Okay. So okay, I just want to make sure that this is the sum I want to look at. Yeah, this is the sum I want to look at. Okay. So the book says that the answer here. Now I'm worried that I actually copied this wrong. Oh no, k is fixed. Okay. So k is fixed. If you had your choice of values of k, which value of k would you like to use for something like this? What would be the easiest value of k to look at? You get to choose any value of k. K equals 0. So if k equals 0, we have the sum, n goes from 0 to infinity, of 2 to the minus n. So this is a geometric series. And so since it's a geometric series, it's the first term, 2 to the negative 0, over 1 minus the ratio, which is 2 to the negative 1. And so when you unwind everything, you get 2. All right? Next one to look at is k equals 1. We have a sum, n goes from 1 to infinity, of n choose 1, 2 to the minus n. Well, n choose 1 is just it's n. How many ways are there to choose one object from n? There's n ways. So n goes from 1 to infinity, n, 2 to the negative n. If I wanted to, could I start the sum at 0? Yes. Because I'll just be multiplying by 0. Now if you think about what's going on here, what does 0 choose 1 mean? Can someone tell me in English what 0 choose 1 means? Yes, try to do it without smiling.
How you can pick an object out of, pick one thing out of 0 objects?
Yes, how many ways are there to choose one object from a set of 0 objects? How many ways can you choose one object from a set of 0 objects? 0. So in fact, n choose k is always going to be 0 if the bottom is less than the top. This is a natural extension of the symbol. Okay? So in fact, we could actually have all of these sums start at 0. We have not done differentiating identities in this class, correct? What I want to do now is I want to show you a really good technique in problem solving to handle something like this. It's one of my favorite techniques. It is extremely useful. Equalities are the bread and butter of mathematics. It takes a lot of work to prove an equality. I realize I'm going to sound like a used car salesman. How would you like a method that will give you infinitely many equalities from a given inequality at no additional cost? Doesn't this sound good? Okay, all you have to do is be willing to be an engineer or an economist. Or a physicist, I think would be close enough. All right. You can, of course, make everything I'm saying rigorous and you can justify this. It's the method of differentiating identities. Okay, so now let's imagine we have the sum, n goes from 0 to infinity, of x to the n. And I'll assume the absolute value of x is less than 1, so I can use the geometric series formula. What would that sum equal? So I've got the sum of x to the n. So what would this sum equal? Yes?
1 over 1 minus x.
Yep, and I'm just going to write it 1 minus x to the negative 1, just to save some blackboard space. Okay? What I want to do is I wanted to study the sum of n 2 to the minus n. Well, if I'm looking at n times 2 to the minus n, the 2 to the negative n looks like 1/2 to the n. So it looks like I want to take this sum where x equals 1/2, but I want to multiply each term by n. I want to multiply the nth term by n. Do you know any process that can give me an n coming down? Yeah, differentiation. All right? What's the derivative of a sum? So the derivative of a sum is the sum of the derivatives if it's finite. And so in calculus class, you prove, if I have f plus g prime, that's f prime plus g prime. If you want to prove the sum of 3 functions is the sum of the 3 derivatives, what do you use? Induction, right? When in doubt, it's induction. We write this as f plus g plus h prime. By induction, well, we now have a sum of two functions. This is f plus g prime plus h prime. But what's f plus g prime? Right. Technically, at this point, I still need to keep things in parentheses, but addition is associative, right? This is one of the times I want associative, not commutative. Parentheses do not matter. And so I get the sum of three functions is the sum, the derivative of the sum of three functions is the sum of the three derivatives. I can do this for 4, I can do this for 5, I can do this for any finite number, but I cannot do it for infinitely many without doing some more work. So if people are interested, I will pass along some notes to justify when the sum can be differentiated term by term. Let's assume we can do that. So if we differentiate term by term, if we apply the operator d by dx, what do we get? So we'll push the derivative inside the sum, and what do we get? So we differentiate. What does x to the n become? N times what? X to the n minus 1. Do I want x to the n minus 1? I wanted n times x to the n. What could I do to get rid of this negative 1? Instead of taking the derivative, I could do a little bit more.
Change the index of summation.
So if I change the index of summation, that will also change this number here, unfortunately. And that would become an n plus 1. So it's a good thing to try, but it's unfortunately not going to work here. Multiply by x. So take the operator x d by dx. When you're doing problems like this, it's sometimes not clear, do you want to do d by dx or do you want to do x d by dx? If I do this, I now have n x to the n minus x, n x to the n. If I do it the other way, I just pull out an x. It's a question of which is easier. And so over here, I now take x, I apply d by dx. I get x times negative 1, 1 minus x to the negative 2. The derivative of this is a negative 1. The negatives reinforce, and I get x, 1 minus x to the negative 2. And then what value of x do I want to take? So what value am I trying to study? What's the value? Well, any value of x is 1, but for the problem we were looking at, what value do I want to take x to be? 1/2. And so that gives us the sum, n goes from 0 to infinity, of n times 2 to the minus n is 1/2 times 1 minus 1/2 to the negative 2. 1 minus 1/2 is 1/2. To the negative 2 becomes 4. 4 times 2 is? What do you notice about this and the answer when k equals 0? Question?
I'm sorry. You said 4 times. You said 4 times 2.
Oh, sorry. 4 divided by 2. Sorry. I have 1/2 times 4. Sorry. 1/2 times 4 is 2. When k was 0, what do we get for the sum? When k equals 1, what do we get for the sum? What do you think we would get when k equals 2? How many people are confident that it's 2? We have 2 data points. And both data points are 2. Is that enough to be confident? All right, so what would we do if we wanted to test it? What should we do next? So if you are suspicious that it's not always equal to 2, what should we try to do? Do another one. So let's look at k equals 2. We now have a sum, n goes from 2 to infinity, n choose 2, 2 to the minus n. All right, what does n choose 2 equal? N choose 2 is? It's going to be n minus 1 over 2 factorial times 2 to the minus n. And now when we look at this, we actually will get a better sense of which operator do we want to apply. If we apply the operator x d by dx, the power of x doesn't change. If we apply the operator d by dx, the power of x changes. I want to get an n times an n minus 1. Do I want the power of x to be changing or not changing? So if I come back over here, if I apply d by dx again, what am I going to get outside over here? So what would I get if I applied x d by dx again? So I apply x d by dx again. The derivative of the sum is the sum of the derivatives. And what do I get now? So I have n x to the n. I take the derivative with respect to x. I multiply by x. What do I get? I get n squared x to the n is now, I've got x d by dx, x over 1 minus x squared. What rule do I get to use? What rule do we get to use for this derivative? Quotient rule. Right? Quotient rule is usually pretty unpopular. Right? Do I want n squared? No, I want n times n minus 1. Now, I could say, oh, well, I could take this, and then I could subtract this, and that'll give me n squared minus n. That factors to n times n minus 1. So if I know this, I could find this. That's a lot of work. For some problems, it's good to do that. But for this problem, it's actually better not to do x d by dx. And so if I just apply the operator d by dx, this becomes n x to the n minus 1. And the only thing is I don't have the x over there. Do I want to have the x over there? No. Because I want to study n times n minus 1 and not n squared, it's actually better not to have the x there. There are some problems where you'd want to study n squared. This is not one of them. And so now, if I apply d by dx again, I get n times n minus 1 x to the n minus 2 is equal to negative 2, 1 minus x to the negative 3 times negative 1. So I get negative 2, 1 minus x to the negative 3. What value do I take for x? A half. And so if I take x equals a half, I get a sum. N goes from 0 to infinity. N minus 1, x, 1 half. So it's going to become 2 to the negative n. So if x is 1 half, I then also have a 1 half to the negative 2. What's 1 half to the negative 2? That's going to be a 4. So I'll have a 4. And this is going to equal 2 times 1 half cubed, which is 1/4. Oh, I'm sorry, to the negative 3. So 8/16. Well, I can get rid of the 4 by dividing by 4 on that side, right? So the 4 goes away. I put in a 1/4 here. The 16 becomes a 4. Is that what I was supposed to have, n times n minus 1? I was supposed to have n minus 1 divided by 2. All right, so I have to put in another divide by 2. 4 divided by 2 is? All right, when k equals 0, 1, and 2, we now get 2. Are you more confident now that it's always 2? Now we've got 3 data points, right? 3 data points is much better than 2 data points. Yes?
So like when you have the 1 minus x to the negative 2,
Yes?
that was x dx.
No. When I did x d by dx, I had x times that.
Oh, okay, you erased it.
And I erased the x. Now I've just got d by dx.
Okay.
Yep. And so for this problem, because I want the binomial coefficients, it's actually better to use the operator d by dx.
Okay.
Right. So much of your life is algebra. Yes?
How did the negative go away when you said?
So I've got a negative here, and I've got a negative here. So when I do the chain rule, I'm going to get a negative 2 coming down, and then the derivative of 1 minus x is negative 1. So it's coming from a chain rule. right, how many people believe that it is always equal to 2, no matter what positive integer k I choose? Is there anybody who's a little bit skeptical? All right, raise your hand if you're skeptical. It's okay to be skeptical. All right, give me a large finite number.
37.
Okay, we're going to fast forward a little bit in time. I have just gone through k equals 0, 1, 2, all the way up to k equals 36. I stopped just below your number, and it's still 2. Are you still skeptical? I saw one person shaking their head. I went to 2013, and it's still 2. Are you still skeptical? Yes.
Are you implying that we should be doing a proof by induction?
So one possibility is to do this as a proof by induction, right? Why might it be reasonable to do this by induction? Well, on day 1 of the class, we prove things by induction. On day n, we prove things by induction, therefore. So one possibility is, can you do this by induction? So that's a great homework problem. I'm not going to assign it. See if you can make the induction work. What if I replaced x equals 1/2 with 1/3? Do you think the answer would be independent of k, or is there something very special about 2? How many people think 1/2 is special? How many people think it would also hold with 1/3? So what I want you to do is I want you to get a sense of things without even doing the calculations. So let's try to look and see what would happen if we did something different. So I want you to build up intuition. So we have a sum, n goes from k to infinity of n choose k 1/3 to the n. And let's take different values of k. So we could do the sum, n goes from 100 to infinity of n choose 100, 1/3 to the 100, versus the sum, n goes from 0 to infinity of 1/3 to the n. So let's just choose 2 different values of k. What's the value of this sum? So it's going to be 1 over 1 minus 1/3. So I get, I think, 2/3 down below, so I think I get 3/2. I'm sorry, 2/3, 3/2. If you think about it, when n equals 0, I already have 1. I'm only, each time I'm taking 1/3 of a step of what I did before, I'm not going to get up to 2. I may be off by a little bit, but 3/2 seems reasonable. What about this sum? How big do you think this is? Do you think that this sum is as large as 3/2? What do you think? So there's a difference between these sums. Here, my coefficient changes. As n gets larger, what happens to these numbers? They grow. See here, all these coefficients are the same, but this has a huge delay before they start growing. What's the first value of n that survives in this? 100. What's 100? Choose 100. So the very first term is 1 over 3 to the 100. So it is possible that this does kick in and it grows enough to take into account the fact that we're starting off so much smaller. If you think about what was going on before when we had the 1/2 to the n, well, the very first term there would also be 1 over 2 to the 100. And so is it able to make up that difference? My feeling is probably not. And the reason is if I put in 1/2, all right, I get that this sum is 2. So I've only increased this by 1/2. Whereas over here, if I go from 1/2 to 1/3, these terms are now significantly smaller. So my gut feeling is I do not expect this relation to hold for all values. I expect it to only hold for 1/2. I think 1/2 is special. And again, this is what I'm trying to do. I'm trying to use these problems as springboards to thinking about mathematics, so that you can look at a problem and get a sense of what does the answer look like, what are the properties, do I expect this to hold, how do I generalize this, what's a related problem I could look at, where is the miracle? So a student came to my office yesterday with a miracle that they found in something that they were reading. I did not do an adequate job of explaining where this miracle came from, but they found this connection of why. Okay, someone's smiling now. They found this connection. They were wondering, why is that connection there? What's going on that has all these values equaling to 2? And I want to show you what's going on. So 2, or 1/2, has a lot of very nice properties. I will show you one of the most important properties that 2 has, or 1/2. So why 1/2 is special. So this is an extremely important property of 1/2. It is equal to 1 minus itself. Do you know any other number that equals 1 minus itself?
It's unique.
It's unique. No other number equals 1 minus itself. Where do you think this might come into play? Yes? This problem, but where might you see things of 1/2 coming into play? What part of mathematics?
L functions.
L functions, but not here. So I did mention the word earlier today. I'm sorry? What word? I'm sorry, I can't hear you. You gotta speak. Okay, what word? What word? I can't hear you. What subject might you have things of 1/2, where something equals 1/2? Yes? Probability. How many of you have ever read Rosencrantz and Guildenstern Are Dead, where they have that huge consecutive string of coin tosses? If you have a fair coin, what's the probability of a head? What's the probability of a tail? 1 minus a half, which is also a half. So in general, if you have a biased coin, not all strings of heads and tails are equally likely. For a fair coin, all strings of heads and tails are equally likely. So imagine toss a fair coin n times. What is the probability exactly k heads? Well, I have to choose k of the n tosses to be a head. Each head happens with probability 1/2, and I have k of them. Each tail happens with probability 1 minus 1/2, and I have n minus k of them. In the special case, when I have a fair coin, these two probabilities are the same, and it combines to be just 1/2 to the n. If I were to use 1/3, I would have 1/3 to the k, 2/3 to the n minus k. And I would get an extra factor of 2 coming out. So this is what's really special about 1/2. So one of the reasons I want to talk about combinatorics is for a lot of these problems, the way to solve them is to tell a story. And so the better story you can tell, the simpler you can solve things. We talked a little bit about stories when we were doing Pascal's triangle, when we did n choose k plus n choose k plus 1 was n plus 1 choose k plus 1. If there's time today, I'll do another story. There is a story going on here for this sum. Okay, it's not always the easiest story to see, but if you can see the right story, you can solve a lot of problems very easily. It turns out a lot of mathematics becomes combinatorics, and a lot of modern number theory comes down to combinatorics. My thesis advisor and one of his postdocs wrote a phenomenal paper. One of them told me it took them 6 months, the other one told me it took them 9 months to figure out exactly what was the correct object to study to make the combinatorics work out. This becomes extremely important. What I want to do now is I want to give an interpretation for what we're looking at. So we're studying the sum, n goes from k to infinity, of n choose k 1/2 to the n. Okay? I'm going to just jump the gun because this is not a probability class, but if you like stuff like this, we are offering probability in the spring. Here's an interpretation. I'm looking at tossing a fair coin, and I want to get exactly k heads in n tosses. Okay? That's what this would be. I'm going to look at it slightly differently. I want to have k plus 1 heads in n plus 1 tosses, and the last toss is a head. So basically, this is the game I'm going to play. I'm going to keep tossing a coin until I get k plus 1 heads. So what will be my last toss? Has to be a head, right? The last toss has to be a head, or you would have stopped earlier. How many of you have taken a stats class? All right. One of the things I love is using stats to, not necessarily to lie, but to slant the truth. Okay? If I tell you, as an aside, a team has won 3 of the last 4. All right, so you know, sadly, it's not the Red Sox. We're trying to figure out how good is this team. If you won 3 out of the last 4, what's your winning percentage? 75%. Sounds like you're a pretty good team. So let's look at some of your last few games. Your last game, 2 games ago, 3 games ago, 4 games ago. Do you know any information? Yes?
You probably know that they lost the last one, or they lost.
Okay, why did they lose the last one?
I'm guessing they lost the last one because they wouldn't have reported won 2 of the last 2, or 3.
Well, if they lost the last one, they've got 3 wins.
Yeah.
And so then I would have said they've won 3 in a row. So you know they didn't lose the last one. So what's the last one? Last one has to be a? It has to be a win. So you know in here you have 2 wins and a loss. Do you know anything else?
The loss can't be first, because otherwise you would have said 1, 3 of the last 3.
Well, if the loss is first, I'm stuck with it.
Oh, sorry.
Yes.
What is it gonna say, like, what?
I was.
I don't know much about sports, but what do you say that they've won 3 in a row?
No, because I know they've won 3 of the last 4. So here's a win. I have 2 more wins and a loss to go in here.
It sounds more impressive to say they won 3 in a row.
But I won't be able to say that. If they had lost 4 games ago, I would have said they won 3 in a row. Because I'm not saying that.
No. Yeah, I was confused about your notation.
Okay, this is going back in time.
So they all.
I thought 1 was the earliest game.
No, sorry. 1 is the game that just happened. So
Probably lost.
they lost which game?
The most recent one.
Well, I don't know about what happened in the most recent because I'm stuck with that data point. I can't, I have to report how they're doing currently. I'm stuck with however they just did. What if I go further back in time?
They probably lost.
Of course they lost. If they had won, what would I have said?
4 out of the last.
4 out of the last 5. So we know they lost this game here. So all of a sudden your team, which initially was winning 75%, now if you look at the last 3 games, they've won 2 out of 3. If you look at the last 5 games, they've won 3 out of 5. You expect to win 2.5 out of 5. It's very easy to slant things. All right? This is one of my favorite ways of slanting things, when you're giving information. Right? I'm telling you now, you've got k plus 1 heads in n plus 1 tosses. The last toss is a head, because we stop as soon as you get k plus 1 heads. Do you expect this game will end? If you keep tossing a fair coin, do you expect eventually you'll get k plus 1 heads? All right. So let's calculate what is the probability we stop after n plus 1 tosses. Well, if we're going to stop after n plus 1 tosses, n plus 1 has to be at least k plus 1, or n has to be at least k. In my first n tosses, I have k heads n minus k tails, and in toss n plus 1, I have to have a head. How many ways are there to choose k slots in these n slots to be a head? How many ways can I choose n of these k slots to be a head? K of these n to be a head. The answer is? So say it. It's n choose k. Right? And now because all strings are equally likely, I have n choose k ways to choose which ones are heads. Each head happens with probability 1/2. I have k of them. Each tail happens with probability 1 minus 1/2. I have n minus k of them. Because 1/2 equals 1 minus 1/2, we're lucky. This is just 1/2 to the n. So this is the probability I get k plus 1 heads in k plus 1 tosses, in k plus 2 tosses, in k plus 3 tosses, in k plus 4 tosses. What's the sum of all those probabilities? Should be 1. Uh-oh, we said it was always 2. I can't swear because this is being recorded. What's the small little mistake we forgot? The last one is always a head. So for this to equal 1, what do I have to multiply this by? I have to multiply by 1/2. All right, well, I can then just put the 1/2 on the other side, and there's the formula. Which proof do you like better, the geometric proof with differentiating identities, or interpreting this probabilistically? They both have their strengths, they both have their advantages. They're both really good ways at looking at problems. The differentiating identities can be used for a whole slew of problems. I'll give you some handouts on that. Combinatorially, most of combinatorics comes down to the following. You want to calculate something. It's damn hard to calculate it. You show it's equivalent to something that's easier to calculate, and then you know what it is. It's telling a story. This is a much easier story to understand, and I can see it just sums to 1. Okay, so for the remaining 10 minutes, I want to do one of my favorite riddles. I maintain a math riddles page. This was actually the very first riddle that I posted. Someone asked this to me when I was a graduate student back at Princeton. How many of you are considering graduate school? All right, the following is actually not a bad description. All right, imagine you have 10 cookies and 5, I'll put hungry in quotes, but it's actually not a bad assumption to just assume a graduate student is hungry. All right? There was a free food email list for graduate students when I was a postdoc at Brown. And they would send out emails saying, at 4 o'clock there's going to be a talk in this department on the following subject, followed by this food. And the graduate students would then look at the email and say, I can listen to that for pizza. Or, wait, they're just going to give cheese and crackers? No, that's not worth cheese and crackers. So they had email. Do they have that here?
Yeah, that's how it is here.
Okay, yeah, so I'm saying, okay, then you're ready for grad school. Now,
They used to have a real lesson.
so at this point, I'm going to specialize to maybe math grad school or physics grad school. I'm going to assume the graduate students are distinguishable. Okay? No. If you're in engineering or bio in a big lab, the graduate students are not really distinguishable. They're all, your lab slave. All right. In math, the graduate students are distinguishable. All right. So I will assume I can tell the students apart. Okay. But I will assume the cookies are identical. All that matters is how many cookies you get. You don't care which cookies you get. Okay. So I want to know how many ways are there to divide the cookies among the people. Somebody give me a very painful way to solve this problem. Yes?
You consider all the possible situations that can happen.
Good. All right? So 10, 0, 0, 0, 0, dot, 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 0, 0, 0, 0, 10. Now what comes next? 9, 1, 0, 0, 0, and eventually, there are a lot of things. Then what comes after 9, 1? Then we have the 8 2s. Then things get interesting. We have the 8 and the 1s. You can do this. I will post today the brute force solution of this. I did not do the brute force solution. I maintain a riddles page. Somebody sent me the brute force solution. I have filed that for teaching. And it's right. And that's actually a fun problem for certain definitions of fun, to go through and see how many different ways can you put H2 among the 5 people? How many different ways can you put 811 among the people? It turns out this is extremely important in solving this problem. So if you've ever done combinatorics, one of the problems you sometimes get is you have the word Mississippi. How many distinct nonsense words are you allowed to form from the word Mississippi? So you can't distinguish the S's from each other, you can't distinguish the P's from each other, but you can distinguish an S from a P. Mississippi, I think, has 11 letters. We have 4 S's, we have 4 I's, we have 2 P's, and we have 1 M. And what you do is you put subscripts on the S's, 1, 2, 3, 4, and same for the others. So you assume initially the S's are distinguishable. And then you divide by 4 factorial to get rid of that specialization, to get rid of that ordering. This is the number of ways to to rearrange the letters. This is a key input in looking at all the different ways to do 811, because it matters which 2 people get the cookie. All right. What I want to do now is I want to show the fast way to solve the cookie problem. And again, it avoids the brute force. It does combinatorics nicely. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 cookies. We add 4 more cookies. And who is my favorite character from Sesame Street? Cookie Monster. The original classic Cookie Monster, not the politically correct bastardization of Cookie Monster. Okay? What is the original Cookie Monster always up for? More cookies, eating cookies. The difficulty is restraining him. There is a clip, I'll try to find it, where Cookie Monster meets the Count. And it's like irresistible force versus immovable object. Cookie Monster wants to eat the cookies. Count wants to count the cookies. They come up with a solution. You can probably figure out what the solution is, but I will post the clip. So we imagine Cookie Monster is here. Cookie Monster eats a couple of cookies. He will eat exactly 4 cookies, and then we constrain him. All right? How many cookies are up to the first eaten cookie? Then 0, 3, 1, and 3. What do those 5 numbers add up to? 10. It turns out there's a 1-to-1 correspondence between the number of ways Cookie Monster can eat 4 cookies from 14 as there are to divide 10 cookies among 5 people. And the reason is, when you eat 4 of the 14 cookies, you've put in 4 partitions. Everything up to the first partition goes to the first person. Everything between the first and the second goes to the second person, and so on and so on. How many ways are there to eat 4 cookies from 14 when order doesn't matter? 14 choose 4. Which, if you do the algebra, is 1,001. More generally, what if we have C cookies and P people? How many ways are there to divide C cookies among P people? C plus P minus 1, choose P minus 1. Now, some of you might object to this division. What is unappealing about this division? Yes?
Some people are sad and they don't get cookies.
Some people are sad and they don't get cookies. Anything else?
Some people got many more cookies.
Some people got many more cookies than others. So, do we want to put in notions of fairness? It turns out it's a lot easier to require everyone to get a cookie than to have bounds on how many cookies people can have. Just mathematically, it's very easy to put in lower bounds. What we're doing is we're actually solving what's called a Diophantine equation. We're solving x1 plus x5 equals 10. Each xi is a non-negative integer. And we're solving the system of equations. And it turns out there's a very easy way to solve this. That's what we've just done. This is a combinatorial proof. There are other ways to solve this. There's analytic methods, which if people are interested about, I'm happy to discuss. You would really find these in a more advanced number theory course. This is where you would get something like Waring's problem, trying to represent